do things with R0, R1, R2. The processor will look in the program status word to find out which version of R0, R1, R2 you're talking about.
Gravity.
That's all.
Yeah, so the bank choosing is only specific for fuse instructions, for the register instructions.
By default, the register bank that's active is register bank 0. So if you say, move the contents of R0 into the accumulator, there's no ambiguity. What happens is basically the processor looks in the program status word and says, which is the register bank I'm dealing with? Oh, it's register bank 0, so it will take that and put it into the accumulator. If you've previously set up the program status word to make register bank 1 active, and you do exactly the same instruction, you say, move into the accumulator R0, you won't get the same thing. If you've changed the program status word so that this register bank's active, it will take that version of R0 and that will go into the accumulator. Yeah?
Would you be able to push from one register bank and then pop into another register bank?
You can always pop wherever yes, you can. I'm not sure why, usually it's a very dangerous thing to be doing, but you can push from one location to somewhere else. Yes, you can do that.
How do you specify which register
Change
bank
the
to
order.
use?
Right. You would, I think effectively when you're doing a pop, what you would do is give the direct address of where you're popping to. So if you wanted to push from here and pop over to there, you could do, first of all, I suppose, I've not tried this, you would push 0, which would do this, and then you would pop into, you want to pop into this location, 8, so you would pop at 8. If that's allowed.
Yeah, I was wondering that if you can change the order, because you said if you don't change the if you change the order, you just get different results. So if you can manipulate it.
Yes, you can, but we don't usually do that. It is possible to manipulate it, and I have seen some special cases where you actively go in and manipulate it, some very clever assembly language programming. But as a rule of thumb, you've got to be very careful what you're doing.
Yeah.
Yeah?
What if you were to go the other way? If you wanted to push from register bank 1 and then pop to register bank 0?
I think they could do that. I don't think there's a problem with that. I suppose you could do the equivalent of pushing 8 and popping to 0. All you're doing is following this by an address.
Okay.
So I haven't got, and I'm pretty sure it's a direct address, so it's basically you could do any, I'll check that by tomorrow anyway, but as far as I'm aware, that you could do that if you wanted to do that. But that's not normally what we would do. There is another very important use for this, and I'll come on to this now, and then, well, before I come on to that, so we have the register banks, and if you're happy not to use register banks 1, 2, and 3, you could probably just leave the stack pointer pointing where it is by default. And when you start using the stack, you'll first of all overwrite register bank 1. If you start growing it anymore, you'd overwrite register bank 2. If you grow it anymore, you'd overwrite register bank 3. If you don't like that and you think you might want to use all of those register banks, you could move the stack pointer to point to the bit addressable memory. But again, we tend not to do that because that bit addressable memory, there's clever things that we can do with it that we can only do with that little block of memory. So we tend to avoid that as well. So a common place that we usually stick the stack is just above the bit addressable memory, because then we have a block of RAM that has no special clever capabilities, it's just RAM. And so it would be quite common to see a programmer write something like this one. Move into the stack pointer 1, not 1F, sorry, move into the stack pointer immediately 2F. 2F is actually the last byte address of the bit addressable memory. So the first value you would push would actually be above that, and it would be location 30 in the general purpose memory. So that would be, now you might, another thing to be aware of, if you do a certain number of pushes onto the stack, the assumption is you know how many pops to do in reverse order. If you pop more than you push, you'll actually cause the stack to go below its base and actually carry on down. And there's nothing clever in the 8051, or most processors, that actually check for that kind of thing. So if you put 4 things on the stack, and you take 5 things off, as far as this is concerned, fine, that's what you want to do. And the stack will have moved down even further. It's up to you, and you as the programmer, to make sure that you're disciplined and you remember how many things you've stuck on it, so you know how many things to take back off it. So let's just so that's why we're seeing this. Now, strictly speaking, this is, if someone's actually done this, like I said, I didn't prepare the slide. This slide is not quite true. They're saying, well, you could use this, initialize the stack pointer with this. Yes, you can, and yes, it moves beyond the bit addressable memory, but actually 2F would have done the job equally well. We've actually lost one location of general purpose memory, because if that's how we initialize the stack pointer, the first place we're going to use is not location 30, it's location 31. So I would say it would be better to write 2F there. Look. That's that point. So the stack grows upwards when you push to it, and it reduces when you pop from it. Okay? And in principle, despite what it says here, you can use the bit addressable memory if you want. It's okay, but we try not to do it. The stack is used as a temporary place to hold information that basically is a group of values we want to store, and later on we want to pop them back out and put them back where they were. That's normally how we use the stack. But you might want to use the stack using push and pop. The computer itself also implicitly uses the stack for something called subroutines, and I'm going to come on to that now, just for a minute or two. Let's leave that for a minute. Let me just blank it. There is a very powerful thing that you can do in the 8051. You may well have a block of code and you want to do a similar operation many, many times in this code. Let's say that in this code you want to insert some kind of delay, and then you want another delay here, and you want another delay down here. So basically you're doing a similar operation many times in your program. Now you could actually write separately the assembly language for each of those delay routines. An alternative is to effectively elsewhere have your special code that deals with the delay, and these things go to it to do this bit of special programming, and then when they've finished, you go back to where you came from, the next instruction. Like a, I suppose it is, yes. It is like a, yeah, it is like a method. So if you like a function, like a method, in assembly language we talk about this thing being a subroutine. Now, in order to achieve this, we're in the main program here, and then we're going to go somewhere else. It's important we remember how to get back to where we need to be. Now, you know that the thing that points to the next instruction in any 8051 program is the thing called the program counter. Okay? So if we happen to be at this point here, just about to go into this delay routine, the program counter will be pointing to the next instruction. We could store the program counter on the stack, so that when we finished here, we know to go back to the stack, recover that address, stick it back in the program counter, and then the program will carry on from where it finished, where it left off. Now, in order to achieve this, to go to this subroutine, there's a special instruction. Basically, generically, the instruction is called call. And there are different flavors of call. The slides have got it wrong slightly again. There's actually 3 flavors. There's L call, A call, and S call, I think. sure about that one. Anyway, there's definitely L call, and I'm pretty sure of that. Anyway, we'll check on the slides. Basically, if there was a routine called delay, you might have something like says delay, and then some code. Elsewhere in your program, you can say L call delay. And then you have the rest of your code here. What would happen is at that point in time here, when you have this call, the program counter will be pointing to the next instruction after this one. That will be stored on the stack. You will then jump, the stack will then, the program counter will be updated with this address. Go to here, start executing this program, and then for a subroutine, it's absolutely essential you finish it with the instruction ret, return. Ret basically says, go back to the stack, recover the address that you find there, stick it back in the program counter, and carry on. If you forgot to put the ret in, then having put the program counter on the stack, it's not going to be recovered, and the program will just kind of carry on down here and do horrible things.
When it's using the stack in that way, does it use it in a separate location?
No, it uses it in exactly the same. It's the same stack that you're using. Now, if you choose to do funny things, such as you put a certain number of extra things on the stack and don't forget to take the appropriate number off, and this finishes its ret, it's not going to have the right value in there, and it's going to load up the program counter with something that it's not expecting. And that's the kind of point I'm getting onto. The stack, there is only one stack in this, and it's used by you doing your pushes and pops, but it's also used by the program, if you like, the 8051 itself, for when it's going to subroutines. So we'll leave it there. Tomorrow we'll recap this again, and we've got lots more assembly language programming to do as well. If you have any questions, you can either ask me